Okay, I'm going to explain the method of cylindrical shells for calculating volumes. So let me just tell you what the region is, what the axis of rotation is, and what the figure looks like. And I'm going to speed this up because by now you guys probably know how to do this part. Okay, here's how the method works. You draw a line through the region that you're going to rotate parallel to the axis of rotation. And you can draw that line anywhere in the region that you like. So I'm going to draw it here. Then we're going to rotate this entire line around this axis of rotation. So this point is going to end up here. This point is going to end up here. This vertical line is going to end up like this. And when you rotate the line around that axis, of course, what you get is a cylinder. And the radius of that cylinder we're going to call r. So this distance is r. We're now going to draw another cylinder by increasing the radius to r plus dr. So when I do that, I get a slightly bigger cylinder. A cylinder with a bigger radius, and it looks like this. Okay, and as with the disk method and the method of washers, as a first attempt, we're going to just try to calculate the volume between the inner cylinder and the outer cylinder. So let me just draw those a little bit more carefully so you can see what's going on. Here's the inner cylinder. That's the axis of rotation. That is r. Here's the outer cylinder. And its radius is r plus dr. And we're interested in the volume between those two cylinders. Now notice something, because this is a curve that's sloping downwards, this height, the height of the outer cylinder, is slightly bigger than the height of the inner cylinder. But in the limit, as dr becomes infinitesimally small, their heights become identical. And when the heights become identical, the stuff in between the two cylinders has the same height everywhere. And what you can now do is imagine that we slice through both cylinders and lay out flat what that surface looks like. When we lay that surface out flat, what we get is this. Where if this is h, the height of the cylinder, then that is h. This is the thickness of the stuff in between the two cylinders, and that thickness, of course, is just dr. So that distance is dr. And that length is just that entire circumference of that circle unrolled to get that length. So if the radius of that circle was r, then the circumference would be 2 pi r. And now it's not too hard to see that the volume of that very thin sliver of a cube is exactly equal to the volume of the stuff that's in that cylindrical shell. So that volume we can write down an expression for very easily. So the volume then, the differential volume of just that tiny cube is 2 pi r, this length times that length times that length. And then going back to the original diagram, if we knew something about the smallest value of r and the largest value of r, we could then add up all of these cylinders and get a net volume V, which would then be the integral from the smallest value of r to the largest value of r of 2 pi r h dr. And of course, as before, the secret here is knowing how this is a function of r. In other words, we want to go back, use the information about the region, and understand how the height is a function of that radius. And once we have a formula for that, we just plug that in h. We plug that formula in h, and we do the integral, and we have the volume. And that's the method of cylindrical shells. In the next video, we're actually going to calculate how h is a function of r.